So the reason that that happens is because the button is debouncing. So when a button is pressed, the mechanical switches or contacts sometimes make contact and bounce off each other several times before they make contact. And the other thing is they may stay connected together for more than one iteration of the loop. So I have a short video of debouncing, which I'm going to play.
Welcome to the Logic Minute. In this video, we will look at a simple method to debounce a signal with logic. When a mechanical switch is actuated, it often produces multiple electrical signals due to physical bouncing of the metallic contacts. The signal to the right shows a typical example of the output of a mechanical switch. Many devices can detect even a 1 nanosecond pulse and would be triggered multiple times by this signal. Zooming out a little bit lets us see the bounces on both the rising and falling edges of the signal. We will keep this signal in the background to compare to the debounced signals. Just by adding a capacitor, we have the simplest debounce circuit. This will work in most systems, but we can see that the initial discharge is not slowed at all, so we're really counting on the switch's first bounce to discharge the capacitor fully. To be absolutely certain that the signal is debounced in both directions, a second resistor can be added. Here you can see that the bounces are filtered out of both the rising and falling edge. One side effect of this circuit is that the rising and falling edges are now very slow, and sometimes non-monotonic, as can be seen here and here. The signal rebounds slightly, which could cause double triggering on a normal CMOS input if it just so happened to fall at the threshold level. The solution is to use a logic device with added input hysteresis, like this Schmitt trigger inverter. This solves two problems at once, providing separation between the rising and falling edge trigger levels to eliminate issues from non-monotonic behavior, and preventing excess current from the slow input edges. Thank you for watching. Please explore the other videos and training material on our site.
Okay, so we can do this in software, and we can also do this in our program. So the video showed you how to do this in hardware. We can do this in Tinkercad because there are Schmitt triggers and obviously resistors and capacitors. So as part of your tutorial, it would be useful to debounce a switch using hardware and software. So again, the same circuit. So now we've got button debounce. Same circuitry. Again, this is in the public domain, this code. Pin 13, pin 2. LED state is high. So the current state of the LED on line 35, the button state, so the current reading from the input pin and the previous reading from the input pin. So we're saying that the last input button state is low and the previous one was high. The following variables are unsigned longs because they are time and they will become large numbers. So the unsigned long is the last debounce time and the unsigned long is the debounce delay. So this is the time that we want to commence to, so that's 50 milliseconds to show that we don't get any flickers in the output. It can be increased, so that's the debounce time. So the void setup. So we've got the pin mode, input, button pin input, LED pin output, and we are switching on the LED pin. This time we are not communicating with the serial monitor. So we are reading the input pin and on line 54 and storing that in reading, and this is an integer. So check to see if you just press the button, i.e. the input went from low to high and you've waited long enough since the last press to ignore the noise. If the switch changed due to noise or pressing, then if reading does not equal the last button state, then we reset the debouncing timer. So last debounce time is millis. If millis minus the last debounce time is greater than the delay, the debounce delay, which is our 50 milliseconds in this case. Doesn't matter what the actual number is because we can change it at the top of the program. Then, if that is true, if the reading is not equal to the current button state, so if we are on or off, then we change the current button state to equal the reading. Only toggle the LED if the new button state is high. So if button state is high, then change the LED state. So LED state equals not LED state. So you're changing it from high to low or low to high. So this time we are pressing for on and pressing for off. So set the LED. So now at the bottom on line 82, digital write, the LED, so switch pin 13 to high or low dependent on LED state. Save the reading. So last button state equals reading. So next time through the loop, it will be the last button state. So let's start this simulation. So as we said, up here, the LED state is high and the last button state is low. So if I press this once, it's gone off. If I press this again, it's gone high. Off, on, off, on. You see it's not going off exactly. So you can have a play around with the values of the debounce delay. So if I stop the simulation and make it as 100. If I make it too high, I'm multiple pressing and it's not going off. 1, 2, 3. Took me 3 presses then, but I need to keep it off. This value needs to be changed dependent on your circuit and your program, because obviously your program, depending on how you write it, if you've got many delays in it, because this program doesn't have a delay in it at all, so therefore we can have a minimum value. So if we change that to 50. Stop the simulation. I just want to change it back to 50 because I don't want it to change that, to lose that number. So this time we can control the button on and off with the LED on and off with the button, as compared to the previous example where we had to press the button for on and let it go for off. There will be two different requirements for 2 different applications. Both seem simple, so the buttons seem simple, however they're different functionalities. So we've got the debounce circuit there and a summary of the code. So in that last loop, if button state equals high and LED state is less than 0, turn the LED on. This is a different one. Let's just go back to the facts. The circuitry in here is slightly different to, in the example, is slightly different to the program listed in the PowerPoint. The PowerPoint code would still work. However, Arduino is live and keeps updating its examples. So when I wrote this, then they changed it, and I've not changed the slides. So I'm sure you could see that this does the same thing, but the previous code is slightly different. So if millie's is minus debounce time is greater than debounce delay, if button state equals high and LED state equals 0, we're doing equals 0, whereas in our example that I just went through, we used not equal to. So it was a simpler if statement. However, the result is the same. You can see there are a lot more conditions here. If button state equals high and LED state is less than 0, turn the LED pin to high, change the state of the LED state. This program is, like I said, it's doing the same thing. However, it is more complex logic, which is important. However, this code, we always want, once we get our code, once we write code for ourselves, it may be in have a complex nature. However, once it works, then we usually simplify it. So this example is if condition, do something, else if another condition, do something else, otherwise do something else, and if none of these conditions are true, not true, do this. So we always want to try and make our coding as simple as possible. I mean, my idea, dependent on the application, I always like to use switch case. But if we have multiple conditions here, like in this example, and here, then obviously, well, more this one, switch case can't be used. Then it's got to be the ifs. Or we write our program in a simpler fashion, like in the example shown in Tinkercad. So the last part of this lecture is matrices, an expansion of array data structure using Arduino. So matrices are an expansion of the array data structure using Arduino. It's an index very much like, a matrix is indexed very much like an array. The rows are indexed first, and then the columns. So we've got Sure, you must have done arrays in MATLAB. So this is a 4-row times 4-column array. It just happens to be a square matrix or array. That's by the by. So these are the elements and the rows. So this is a 0, 0 up to 0, 4, 3, and this is 3, 3. This one would be what? Difficult because I don't have any. I can't ask you any questions. So this is the 0, 1, second row, first element. This isn't the value in the array. This is the indexes or the indices. The value could be a number, a letter, 3, 5, 2. So array 0, 0 equals 4. So I think we've already introduced the concept of arrays previously in this group of videos and slides, and we use a nested loop. It's simply one or more for loops inside of curly brackets of another for loop. So essentially what we have is we have a for loop for I equals 0 to x in steps. We have, and then another for loop j equals 0 to x in steps. Open that for loop, close that for loop, and close that for loop. So the I would be the rows, and the j would be the columns, and the variable would be ij. But we will see this in this example, in the following example. Okay. So what I've done here is we've connected the LEDs to multiple Arduino pins. You can purchase arrays. Excuse me. Yes. Array outputs, LEDs or other components can be purchased. However, this is just showing the concept using multiple LEDs. So we have a 3x3 matrix. So we have the first LED. Oops. Connected to pin. We're going up to pin 2. So in our array, which is 1, 2, 3, 1, 2, 3, 1, 2, 3. First LED is connected to pin 2. The second LED, which is this one, is connected to pin 3. This connected to pin 4. This LED is connected to, on the orange wire, pin 5. This LED is pin 6, 7, 8, 9 and 10. So I'll check this one. This LED is connected to green wire, which is pin 10. For each of the LEDs, they cannot not connected directly to the pin, they're connected through the resistor as shown, and the other leg is connected to the ground, which is connected here, up here, to the ground pin. So element, this is then shown. So input pin matrix is 3, 3, because that's the size of the matrix. 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, I've showed this image here for reference. This can be written in the following 2 formats in the sketch, because the Arduino just converts it into hexadecimal file. So these 2 formats can mean the same thing. So we've got the curly brackets for the matrix and the curly brackets inside to denote each row. So 2 is indexed by 0, 0. 6 is indexed by 1, 1. And 8 is indexed by 0. Sorry, 2, 0. It's getting it the wrong way around. And here's the other examples there. So as previously mentioned, this is done by, we access each of the LEDs by 2 variables, I and J. So we go for integer I equals 0. So start off at 0 up until while I is less than 3, and add 1 to I each time. So the first time round the loop, it's. Then we have J goes from 0 to less than 3, and we increase J once every time we go around the loop. So the first 2 nested for loops are setting all the output pins from pin 2 to 10 as output. So pin matrix I is the row and J is the column. So row 0, column 1, then J gets, so that's round this loop once, then J gets incremented, so it's still row 0 and J equals 2. Sorry, this is 0, this is 1. So first time round the loop, J equals 0. Second time round the loop, J equals 1. Third time round the loop, J equals 2. However, when we increment J to equal 3, which happens here, then this condition is no longer true because J is not less than 3 anymore. It is equal to 3. So therefore, this iteration, we jump out of this loop. So we've repeated this loop 3 times already, and now it's no longer true. So we jump out to the outer loop of the nested loops and then increase the row number to 1. So this is our second iteration of the loop. So we would then go to column 0, column 1 again, and column 2. And then this would equal 3 again. So this would jump out. So then this would then go to its next iteration, which is row 2. And then we'd go 0, 1, 2. So we're essentially following this diagram here, which is what I've just written on here. So we are setting all of those pins as output. So this time we are turning, all this program is simply doing is showing you how to index to each LED. So it's how to, all we're going to do is turn up the particular LED on to high for 100 milliseconds and then turn it off again. So this will show how we are accessing the LEDs in this particular fashion. So we will go to the Tinkercad example. So obviously we've got the full listing of code here. In pin matrix, delay time. So I've set the delay time as 1000. Setting the pins to output. We will see in a later recording how we can do this a lot quicker by using C. So then we're simple, just as we wrote in the PowerPoint, the program. So start the simulation. You can see this one, this one, this one, this one. Okay, so that will keep on going and going and going. Stopping that simulation. And that is the end of this very long lecture with 106 slides. I've tried to split it up into smaller sections for you, and I look forward to speaking to you. So we've learnt about programming in the IDE, looked at common Arduino functions, simple blink programs, conditional programming, digital, and arrays.